In this video, we're going to look at how to calculate the moles of a gas if it's not at STP. The ideal gas equation is a combination of three laws: Boyle's law, Charles's law, and Avogadro's hypothesis. So let's look at how it's derived. Now, according to Boyle's law, volume is inversely proportional to 1 on pressure. And now if we look at Charles's law, we know that volume is directly proportional to temperature. Now you have to remember the temperature is in the Kelvin scale. Now if you look, now what we can do is we can put these together. You can see that volume must be proportional to the temperature on the pressure, or we can say that P times V is proportional to temperature. Now, according to Avogadro's hypothesis, the volume is also proportional to the number of moles present. So now what we can say is that volume is proportional to number of moles times the temperature over the pressure, or pressure volume is equal to R, which is the gas constant, times the number of moles times the temperature over the pressure. So how do we calculate the gas constant? So to calculate the gas constant, we know that the gas constant R is equal to P times V divided by T times N. And we know that for 1 mole of a gas, we can calculate the gas constant would be equal to R at STP is 100 times 22.71 divided by the temperature is 273.15 times 1. And this comes out to the magic number of 8.314 joules per Kelvin neg 1 per mole neg 1. Now, you don't have to remember that number. You can actually find that number on your data sheet. So the ideal gas equation ends up being P times V equals nRT. And we're going to be using this equation a lot because more often than not, the gas is not at STP. So what do we have to remember? We have to remember that the pressure must be in kilopascals. We have to remember the volume must be in litres. The gas constant, which is 8.314, you get from the data sheet. And the temperature must be in Kelvin. So you're always going to have to convert your temperatures to Kelvin. So let's try an example. You've been asked to calculate the number of moles in 5 litres of helium gas at a pressure of 120 kilopascals and a temperature of 25 degrees Celsius. Now the first thing we're going to have to do is convert our temperature. And remember, to do that we have to convert to Kelvin. So the temperature will be equal to 25 add 273.15, which equals 298.15 Kelvin. Now that we've worked out the temperature, we can work out the number of moles. So PV equals nRT. Now, you can either substitute first or you can rearrange first. So I'm going to put my numbers in. I'm going to substitute. The pressure was 120. The volume was 5, is equal to the number of moles times the gas constant, which I get off the data sheet, times 298.15. Now I'm going to multiply that out. That's 600 is equal to the number of moles times 2478.8191. So the number of moles must equal 600 divided by that, which equals 0.242 moles. I'm just going to quickly check my significant figures. I've got 1, 2, 3 significant figures, so that's finished. Now let's try a harder example. This time we've been asked to find the volume of nitrogen gas if we've got 30 grams of nitrogen gas at 110 kilopascals and a temperature of 50 degrees Celsius. So to start with, we haven't got the number of moles, but we can find it. The mole is a unifying concept. Because we've got the mass of nitrogen, we can actually find its moles. So we start by saying the number of moles of nitrogen is equal to a mass over a formula mass. Notice I've written the formula I'm using, and I'm telling my marker exactly what I'm doing. It is equal to 30 divided by 28.02, which comes out to being 1.071 moles. Now we can find the volume of the gas. But before we start, we must find the temperature in Kelvin. So the temperature is equal to 50 add 273.15, which equals 323.15 Kelvin. Substituting into PV equals nRT. We know the pressure is 110 times the volume equals 1.071 times 8.314 times 323.15. So the volume must equal, rearranging that, 1.071 times 8.314 times 323.15 divided by 110, and it comes out to 26.2 litres. Checking, this has got 1, 2, 3 significant figures, and my answer is also in 1, 2, 3 significant figures. Now I need you to try some yourself, so go to the OneNote, try kinetic theory, calculations, ideal gas equation, and I've put some worked answers on space.